All right. Well, thank you all for joining me. My name is Christopher Craig, and I'm from the Vulnerability Science Research Group here at Oak Ridge National Labs. That's ORNL because we love acronyms in the U.S. government. And I'm here to give a talk on symbolic execution, or SymEx, or SE, or any of the variety of permutations that's used to talk about it. And the name of the talk is actually a bit of a kind of inside joke. So folks within Oak Ridge are typically from a career science background, career research background. And so when you give them an opportunity to talk, they typically have extremely overblown, hyperbolic titles, which I gave the same talk to internally, and that's kind of the riff using constraint solvers for vulnerability discovery, software, like all this other stuff. And so you typically see that kind of overblown in a lot of research papers or IEEE papers. So it's kind of it's a dumb in joke that's not landing well. But regardless, I'll begin. Also, I'll start chirping on Discord after this. So and I've been kind of chirping on Discord the entire day. So if you don't be, you'll see me around. So don't worry. So here's a basic overview. We'll be talking about SymEx, specifically CLE and Anger, two of the more, I'd say, popular symbolic execution frameworks. After that, I'll begin discussing what I've kind of been doing with it, which is the rehosting problem. And I'll be discussing the nature of the rehosting problem and one of the most predominant tools used to solve it, which is Panda, an extension of QEMU. Followed by my novel work in constraint graphs and constructing constraint graphs, and then kind of an allusion to future work and kind of where things could go from here. So here's the bio slide. Who am I? Who cares? No one, you don't care. You don't care at all who I am. It doesn't matter. I am the machine that delivers knowledge. The biggest point of this premise is that, or the whole point of this talk is that this is a new technology, or at least a new framework that's not being used actively for source code analysis or for software testing. And it really should be, because it solves unique problems. And I'm just here, I'm the person that's here to deliver that to you so that you can ingest it and then go to CLE, Anger, or any of the other frameworks and begin doing the good work. That's all I'm trying to do. If you are still curious and you think this person who put a bio slide saying, well, this isn't a bio slide, this is my contact information, Craig C. at Oak Ridge, ORNL.gov, or if you want a very informal, I know we just had a talk on personal marketing and I checked my Twitter page and it is not very good for personal marketing, an informal contact list, you can just hit me up on Twitter, because I had a blog and deleted it because managing a blog is a lot of work. So let's talk about symbolic execution. All right, let's talk about it. So what is SE? It uses the constraints of a specific variable to generate test input. Full stop. That's what it does. But why should you care? Why should you even bother with it? Well, it gives you unit tests for free. And I'll go through an example of that specifically with CLE on how it can be used to generate novel and unique unit tests, right? So how does it work? What are you talking about? Well, it's much like an algebraic equation, and I have a very, very simple example kind of following this, where it goes through kind of the natural intuition between using a solver in order to solve for unique code paths in code, or unique code paths. It's pioneered by Z3, Meta SMT, and STP, which stands for Simple Theorem Prover. These are all constraint solvers or theorem provers that lie within the heart of these symbolic execution frameworks. You don't really need to go too deep into them in order to use them proficiently as a security researcher or as a software tester, right? Like if you're writing source code or you're the head of a group that is working on resilience within your source code tests or within your source code repository, this can be something that's easily thrown into your CI in order to, or your continuous integration framework. Sorry, I have to explain all acronyms as I say them. Continuous integration framework in order to make your code more robust. This is something that can be easily utilized for that. It's also very good as a bug finder, and I'll have an example, a few examples of those, because that's kind of the whole point, right? So also a good note, this comes from a solid pedigree, or at least symbolic execution. It was used in the DARPA 2016 Cyber Challenge in tandem with fuzzing. And you're gonna hear me go back and forth between fuzzing and symbolic execution, or SE, a lot. And it's because they're two sides of a very, very similar coin. So a basic example, right? You have x over 3 plus 23 equals 38, right? Well, we know how to solve this. If you have taken algebra, what you do is you want to solve for x. You want to solve for x. Well, how do you do so? Well, you subtract 38 by 23, and then you multiply that result by 3, and then eventually you get 45. Now, how did you know how to do that? Well, I've taken algebra. I know. Well, what algebra essentially, like the path that you take in order to solve this, it all has to do with the constraints that you have placed upon x, right? X is divided by 3, and then that result has an additional. You add 23 integers or an integer of 23 to that resulting value, and that gets you 38. Those are set, and there's a single integer that can solve that problem, right? So like, okay, well, you kind of reverse it. You go, well, if I subtract 23 from 38, and then I multiply by 3, that'll cancel out the division, and then eventually I get my number. That sort of intuition is the same sort of logic that goes into constraint solvers in order for them to go through their hard work and figure out what the variable at that particular point in time can be, right? If we look at another example of this concretely in software, right, we have this get sign function, which takes in an integer, all right, it's a signed integer. It can either be 0, greater than 0, or else less than 0. Well, you intuitively know that those are the 3 unique code paths that that variable could possibly take, and it takes you to 3 unique code paths. That same intuition isn't lost when you start diving into source code. And if you wanted to find a unique input that would get you, let's say, to that else branch, like the last else branch, but there were a lot of constraints placed upon, let's say, integer is not an integer, but it might be the result of a deserialized object, and, things like that, things of that nature, you might need a little bit more work to see if this is actually reachable. And reachability is a key part in developing a robust and reliable exploit. So, all right, so the more astute of you will recognize that this interaction is very akin to fuzzing, right? And I mentioned that there's an analogy between that and fuzzing, at least through the lens of like software testing. So what fuzzing does is it generates a unique input, or generates generates input for a specific piece of software based on a corpus of information, based off of some sort of knowledge or mutation or input vector or seed a priori. After that, it generates inputs and whatnot in order to explore code paths within your software. This can either be done statically, a la libfuzz, or it could be done dynamically, looking at AFL and some other stuff in order to just, look at an input and then just, hammer it with a bunch of permutations. Symbolic execution works in a different light. Remember that previous example that we used with algebra. It actually generates the input for a variable based on the constraints placed on that variable. And you might think that's very good, like libfuzz does that statically, and maybe I could do this statically, but I don't know how I can use this dynamically. Well, it turns out you can through some very creative workarounds, and there's a reason I call them frameworks as opposed to just an SE tool, right? You can actually use symbolic execution dynamically. And I'll go through an example of that in a minute, but that's kind of that's the separate side of the same coin, right? Fuzzing, you mutate input in order to explore code. Symbolic execution, you look at the code and you target a specific variable to get to a specific place, if you want to think about it that way. So yay, source code. Everyone loves a slide full of code, right? It's so easy to parse, it's so easy to make through. No, but there's no need to get super antiquated with it. This is a lovely contrived example of a simple example where fuzzing would be something that you would think, oh, I'm just going to go ahead and fuzz this to figure this out, where actually symbolic execution can be a much more targeted way to get to that specific variable. For example, we have our check root password hash, right? It's our library function. It does what's advertised. It takes in a user ID and then a char star pointing to the password. It checks for a specific admin ID. It short circuits if it's specifically a value, in this case 31337, and then returns 0, right? Then we have our authenticate function, which calls check root password. If the return value is error, right, not 0, but error, some other predefined constant, then we go access denied. If not, it's going to go through the work of finding the user info. In this case, if you were to fuzz this, right, you'd have to permute the user ID field, possibly the password field. There's a lot of things that you have to check and interrogate. If you were using something smarter, let's say libfuzzer, it might figure out that it's looking for a specific constant. But if it's programmatically derived from some other things, that would be really difficult to try to fuzz, right? You're just guessing in the dark for some integer. Whereas constraint solvers and SE would specifically look at the user ID field, figure out that its constraint to that path is 31337, and set it to that variable if you wanted to get to the return ID 0, or the return value of 0. You specifically target that code branch. So that's an example of how you can use symbolic executors, like just kind of conceptually, as opposed to fuzzing, how you select that particular tool for that particular problem. All right. So say we wanted to look at this dynamically, like how, oh, never mind, I already moved through that. All right, so we've looked at how we would conceptually interrogate a piece of software with a static or with a symbolic execution framework. So let's look at it statically. CLI is a symbolic execution framework. It uses source code. So it needs source code, a la libfuzzer, right? Not all fuzzers need source code, but good ones do. And it uses LLVM, which stands for low-level virtual machine. You can think of it as an IR without getting too into compiler nonsense. It basically takes the software, it takes the code that you've written or that you're observing, puts it into an abstract syntax tree, puts it into a big old tree structure so that you can programmatically navigate it. That's high level, but that's essentially how LLVM kind of operates. And there's a web demo of CLI if you wanted to go ahead and just ignore this talk and start playing. But in the meantime, let's look at a more concrete example. So we have that get sign function we've been poking at all this time. And so let's say we wanted to use CLI to generate those unit tests, as I was talking about earlier. Well, in order to do so in CLI, all you have to do is say, well, I have an integer of A. I want A to be a symbolic variable, and I need to cap it at a certain size, so that way I know that my program is going to be compiled with a certain thing. And in order to use this, I believe you have to use a specific version of Clang, which I think is the more popular LLVM entry-level way of getting at this, and CLI. And then you can add the function CLI make symbolic, so it turns A into a symbolic variable, meaning it can be anything, right? It doesn't have to be specifically a set integer. It could kind of be whatever it feels it needs to be. And then you execute, then you compile and execute this software. So when you do so, you get, let's see, you get this CLI getSign.bc. This output file is the result of CLI. So when we run CLI, it tells us that the number of total completed code paths and generated tests, right? You see all these generated tests. These generated tests you can actually execute and interrogate individually using a thing called the CLI test tool, right? So CLI test tool will sit there and go, all right, so you wanted to generate a specific unit test. You wanted to explore this specific code path using this specific variable. Well, I attached here, and these are the inputs that I use. These are the actual bytes that I use to generate to explore this specific code path. And there you go, unit test complete. You've took no time at all, and in, what was that, 2 lines of C? In 2 lines of C, you've written 3 unique unit tests, 3 novel unit tests that explore all the code and have guaranteed 100% code completion, QED. But as always, there's more nuance to this, and aside from maybe a very contrived example, let's see how this could be really, really, applied. So let's just say that we have a parser for a regular expression, right? We're supposed to be attaching this library to our code. Someone said that there's a bug in it. You're like, well, I don't know where the bug is. Well, all right, aside from analyzing it concretely, I'm also supposed to write unit tests for it. Geez, this is a lot of stuff for this little fuzzer. So let's just go ahead and use CLI for it. This is some library code. We'll be evaluating it, so there's no real need to get deeply antiquated to it. Match star matches a star of a regex, so it matches any character but null. Match here compares the current character pointer to the defined regex, so it compares it to that specific regex value. And then match is the high-level function that calls each of the subfunctions. So we don't have to get super involved into each of these particular functions, right? So let's say you wanted to fuzz it to figure that out. Well, there's a large number of input possible strings that you could put to fuzz this. Even if you define the size at 7, that's 7 versus all possible ASCII characters. Sure, that's feasible, but you're essentially just vomiting information into your software. You can't make any guarantees about it. It's really, really difficult to do. And if you get a crash, well, you need to record that crash. You need to make sure you observe it. But what if our goal isn't to test all of the input, right? Let's say we're dealing with some, technically I think this is polynomial solvable if the size is 7, but let's just say we're dealing with, we're just trying to get complete code coverage. We don't necessarily care that we've used all novel inputs. At certain points, we're going to get overlap, right? Pigeonhole principle. We'll start hitting the same code paths over and over again, even with 2 different inputs. So let's just go ahead and, oh, I think my headset went off. I'll keep talking. Let's just go ahead and, oh no. Okay, I got it. Yeah, battery. Come on, baby, come back to life. All right. So let's just say that our goal is complete code coverage, right? Well, how will we accomplish that? Well, we'll do the same thing we did earlier. We'll make a specific variable symbolic, right? In this case, we use a symbolic variable, and then we'll try navigating the code with that symbolic variable, having it, basically be like Play-Doh within a key, right? Or within a keyhole. You just mush the Play-Doh in, it takes the shape of the particular object you're looking for, and then we'll use that to kind of find our way around, right? So in this case, we make RE our symbolic variable. We'll follow any constraints placed on that variable. And so what are the possible code paths that we'll hit, right? Well, in this case, there should be 3 code paths in the match function, right? We either match here, right? Or we either hit this if condition or we don't. And then if we are in the do while loop, we'll either hit this if condition or we'll fail the do while and just jump right out, right? Because if we hit this do while, we're going to be stuck in this loop until we eventually fail out anyway. So we have 3 up front, and then we have 1, 2, 3, 4, 5 in the lower function. So we have a total of 8, right? 8 kind of unique code paths that we're kind of navigating. And hopefully, if we just hit all 8 code paths, we're kind of done, right? We'll have RE mutate and do all this other stuff and figure out all the constraints to just target those specific code paths, and then we'll be finished. It'll run, but we have a problem. CLI does not like this. Why doesn't CLI like this? What happened? Well, what we have is, and it's pointing out, and this is actually very good if you wanted to use CLI as a kind of bug finder and bug hunter, because what you have is a runtime error. You don't have a compile time error. It's a runtime error. Well, why not? Well, what happened on regex CP line 24 and 26? If we go to the right-hand side and we look at the match here function, it's using a direct reference, right? It's saying RE of 0. Well, I don't see the problem with that. We initialized this with a size of 7 earlier, right? Even if it's junk, it should be full of something, even if it's nothing, right? So what's the problem? Well, the problem here is that we actually have, and you can consider this either a failure in the test framework or not. If you feed this character strings, and if you try to analyze this directly, all of your RE input would be null terminated because it would be a C character string. The fuzzer doesn't care, right? The fuzzer doesn't care at all. It'll just start hammering through all this code. And so you could find this code dynamically if you just completely randomized all of the inputs, which is what this did. And if you don't have null terminated strings, it turns out that these 2 direct references on lines 24 and 26, it'll hit. You'll get out of bounds errors, and then you'll abort. So let's say we want to do a more thorough fuzzing, we want to do a more thorough evaluation. We can actually add additional constraints to our variables, right? So is this a failure in our software, right? Yes, maybe. Or is it a failure in our test handler? Say this code wasn't reachable, right? Or it was automatically null terminated by an SN printf, not SN, well, yeah, SN printf or stir n copy or anything that guarantees a null character at the end of the buffer, right? The character buffer. Well, then you're absolutely going to hit, you're not going to hit a null terminator here. Your test handler doesn't accurately represent the environment. So we need to fix our test handler. We can just throw in our own constraints. We can do whatever we want. So to fix that, we throw in our own valid constraints, right? So in this case, we make RE symbolic as we did before. This time we set the size -1 to be null concretely, or you can actually use this CLI assume function, which implicitly drives in a constraint that you define yourself. And so with this, you are now in full control of the fuzzer that you're generating, not the fuzzer, the symbolic execution framework that you're using in order to interrogate the code, right? You're in full control. And the output for this is wild. It runs for a long time, but you do get code completion with this because it does interrogate all the stuff. And and figures it out. And it's only 8 unique code paths, so it's pretty quick with it. All right. So now that we've figured out a static way of using symbolic execution, let's look for a more creative application. Maybe we can use it dynamically. Well, in that case, you're going to need something like Anger. Anger is a Python framework for analyzing binaries, combines both static and dynamic execution, which they call concolic execution. I will not, this is a more religious debate, but between symbolic and concolic execution, but it makes it applicable for a variety of tasks. It's geared for code exploration and dynamic code exploration, right? And I'll go through an instance of this and how it goes through it. But it accomplishes this through CPU emulation. I think specifically Unicorn is what it uses under the hood, and it is pretty cool. It allows you, it uses Unicorn basically to get at and identify variables that it wants to make symbolic, even without knowing how the source code is generated or constructed. And it uses these CPU emulators to just kind of immediately become a man in the middle. It's very good. And it uses Python, so it's pretty simple to program. So let's to make analysis a little easier, right? Let's look at our getSign function, but we'll add some print statements after each to make it a little easier to work with. And in this case, we will not be looking at the source code. We'll explicitly be working with the compiled binary, so we won't know any of the source information prior to this. So, right, we'll add these print statements and then we'll go forward. So, all right, well, let's just go ahead and write some Anger code in order to explore the code, right? So in this case, we want to programmatically explore it. So we'll define and import the binary as a project within Anger. We'll set up the symbolic variable, defining the size, because it's very important that you set the correct size for a symbolic variable. You want to mutate stuff, but you also want to constrain it. There's a variety of issues you can get into without it. It sets it up as a BVS, which I think is a bit vector symbol, and we're using Clarity, which is its kind of API between Z3 and Python in order to set up the symbolic variable, set up the project name, and then we're going to call it, and then we'll set a specific entry state, right? Just start at the start. So now, with all that said, we're going to run what's called a simulation manager, and this is what executes the code. This is what executes the code dynamically. So it just kind of goes through and turns and executes the code. And in this case, we want to use the depth first search exploration technique in order to navigate the software, right? So that's all it's saying. So basically, we import our binary, we set up our symbolic variable that we want to mutate and basically be the clay through the keyhole. And then after that, we set up a simulation manager, which emulates the CPU, because we've only done 3 things so far. So now, what we'll do is we'll make sure it's only printable to ASCII characters, right? Only visible ASCII characters, simulating, let's say, a typing environment, right? We will then set our end state, right? Remember I said that Anger is primarily used as a binary exploration technique. And commonly, if you're doing exploit development, reachability is a big problem. You can find some sort of super crazy contrived error inside of, let's say, a parser, but you don't know if you can generate any input to actually get there. Right? You're never sure. This will allow you to interrogate the code and generate the proper inputs in order to target that specific line of code, in order to make sure that you, while you're executing it, can in fact reach that. It's very useful. So in this case, it sets up that environment. It says that if inside of the POSIX environment, which we get from those print statements, inside of our standard out, if we notice in standard out, we see the word negative, right? We see negative, then we'll jump out. Right, we'll just hop out. And so, okay, that's cool. If we see a negative value, we'll jump out. And in this case, we'll, yeah, it's set up in the Lambda function we have defined. I don't have the line numbers, but it's set in the Lambda function. And then after that, we will set our print statement. Yeah, the found solver eval will evaluate until that point. So that's the premise. All right, and so then we'll execute it, and you can see, all right, getSign, we're running getSign. It's a 32-bit bit vector that's going to be mutated and munged around with, and it starts at a simulation state at the program entry point, executes until it gets to an output simulation state, specifically targeting that negative value. And in this case, hey, it's printed negative, and that's exactly what we wanted. And if you notice, we got to this statement using the negative value -2m+, which is interesting because what it essentially tells you is that you can input a variety of characters after the -2 and still have that integer be interpreted as, or still have that string be interpreted as a negative value. So it's probably using something like A to I or something like that. So it allows you a little bit of flexibility and a wider range of inputs to get you to that value, right? Like proper with fuzzing, you can hit that target a variety of ways, and that tells you some information about the program. And same thing here. So now I'll kind of switch gears. So now that we've talked about two specific symbolic execution frameworks, CLE, which works on static, right? You need source code, works statically, you need source code, and Anger, which can work statically but also works dynamically, and you program it in Python and you use it to kind of actively explore your code. There's a particular problem that's interesting, at least to Oak Ridge National Labs, and that's the problem of rehosting. I think Oak Ridge and our partners up at MIT Lincoln Labs. And it's rehosting. The objective of rehosting is to get a high fidelity emulation of arbitrary firmware divorced of its original environment. You want to think of this like a head in a jar. So the goal is to say for a particular proprietary device or IoT device or something like that, that might be mission critical, right? You might only have 3 of these. You want to see if it's vulnerable to particular hardware testing and stuff like that. And the fidelity required to make a digital twin or something of that nature is immense, right? Because those are going for the most high fidelity emulator you can possibly muster. And that's too much typically. So what if you just wanted to get the firmware running? What if a subset of the full feature set is applicable? Well, then you might want to rehost it. You might want to take the firmware out of that and see if you can get it running or in an emulated environment. Typically, these are accomplished using QEMU, Unicorn, but and there's a lot of impediments because you don't actually have the physical device. So there might be things, for example, specific flags embedded in VRAM before the whole machine is booted up. It's looking for specific values in memory that you can't access and don't know. It might be looking for specific peripherals, right? Like it's trying to interrogate whether or not it has the right USB drivers before it even starts, or there's elements in flash, etc. And so there's a lot of impediments to doing that. But what if we were able to have a callback framework in order to actively patch, like monkey patch the emulator as it's executing? That's where Panda comes in. Panda is an open source platform for architectural neural dynamic analysis. Very cute name. Tim did a great job with that one. We are friends, us at Oak Ridge are friends with the guys and active developers of Panda. We meet with them regularly, and it has the ability to kind of record and replay execution frameworks. So if you wanted to interrogate how typically it's very friendly with Linux and x86 systems or x64 systems, but it actually it's starting to open up its doors more to ARM32, and like ARM64 and MIPS architectures. But it provides a Rust-in plugin architecture. So what happens is it hits a certain stopping point, and you want to write a specific plugin, halt execution, do some stuff, and then continue execution. So it's actually really good to kind of monkey patch and work your way into a rehosted environment, right? Because you want to be actively, dynamically exploring the code and figuring out what's doing what and looking around the firmware as it's being emulated. So in this case, I've been talking for a long time. This is kind of the part where I'd stop and ask for questions, but there's kind of no one there. So I'll keep blazing through. I don't have Discord up, so I'll hear all the questions in a minute. But please don't hesitate to just type them in whenever you can. All right, so I actually was given a specific example. So you're like, that seems very contrived and very specific. When would I ever need it? Well, here is one. This is an ARM Cortex-M firmware specifically built for CTF in this case. It reads from system clock, and it's looking for a very specific value from the clock in order to return a flag. Okay, well, what are we going to do? Well, the only thing you were given was the firmware. You do not have the driver to talk to the specific system clock it's trying to execute to. You don't have access to its proprietary information. And in, I think, one case, it can't be easily opened in Ghidra. Maybe I've not tried IDA Pro specifically with its great decompilers, but if you try to open this in Ghidra, it will vomit. It will actually explode, specifically because I think it's compiled in Rust to try to further obfuscate anyone trying to directly look at and interrogate the flag from strings. So what do we do? Well, let's take a closer look at it. If we observe it as it's executing it, we notice that it has a very, very simple pattern. This is a very, very an imperfect representation of the control flow graph, which I will have represented in a minute, but this is kind of a basic approach for it. So it does this IO read, specifically looking for the system clock, and it searches for a value. After that, this says device not found or another IO read. Okay, well, this is through either kind of fuzzing it or testing it or constantly running it. We're observing these types of patterns. So it goes through another IO read, then it fails to initialize, right, if it doesn't have the correct value. And then it does another IO read, and then after that, it seems to be checking for certain values after the clock has been continually reset. And so we're like, well, dang, okay, so I can solve this with Panda, right? And what I'd love to do is interrupt the IO read and return a value of our choosing, right? So you could actually halt. Say you ran it in Panda, you stopped execution at a certain point, specifically after the IO read, took the return value from the clock, made it whatever value you wanted, and then gave it back to the program to continue executing, right? So you halt execution, look at the return value from the system clock, modify it, return. But that's akin to fuzzing, right? That's just searching a specific space because you don't know what the actual value should be. You can't even crack it open in Ghidra to actually interrogate the constants it might be compared to, or worse, it's programmatically generated. So what if we just use the system against itself? What if we use symbolic execution in order to do so? Well, what we did was we worked on a platform called Angrypanda, which basically took the firmware that was executing. As you see, we emulate the hardware, then we emulate the firmware, and Panda has in and of itself a virtual memory address space, right? So what we do is we intercept after the IO read, and we can observe the return value that was set for that value. So we create our project, create memory from Panda. So we copy the virtual memory. I think in this case, we copied, because it was a Cortex-M firmware, we could copy a huge section of virtual memory over, because you do run into a variety of issues with virtual memory and having to make frequent callbacks, and page tables will be a big impediment to this. But if the application runs within 4K, you should be fine. But we can copy memory back from Panda, and then we do what I'd like to call, technically is speculative execution, because what you do is you halt at that space and you say, all right, this is the return value I got. I'm going to make that return value symbolic. And then I'm going to say continue running for some number of simulation steps. Continue running blah number of translation blocks or steps of execution forward using the symbolic variable, and tell me what your states are. So at this point, you begin to explore, right, the code dynamically because you halted execution, and now you have this symbolic variable that's just mutable and whatnot, and exploring the code and fuzzing the code, or fuzzing, but symbolically executing the code and going forward. And you can now observe all of the states that it found that it was able to return to within a certain number of constraints, and it uses those constraints in order to get there. So after that, you find one that you like, and you take that specific value and return back. This work was pioneered by Andrew Fasano and at MIT Lincoln Labs, and I should also say Chimoko Ballo was also responsible for generating the CTF framework. I think he solved it entirely in Panda, but Andrew found a way to use Anger for it, and I took it and did a few extra steps with it from that point forward. So after that, we return, we select our desired state, we solve and cache the constraint solutions, right, for later in case we want to use them, or we return to the specific state later. We can cache that, we can modify it, but we're programmatically exploring this code as we want to, because we're monkey patching it as we're executing it. So here's a live example, right? Do I have to click play? I do. So here's a live example. There I am running the actual executable, and then you can see it's a QEMU ARM system core chip. It's using QEMU to emulate it because it's actually for an ARM chip. And so it tries to execute, looks at the clock, and the clock is not the correct value it's looking for. And it takes no input. You can't use any specific input for it. So it's not like you're going to fuzz this value, right? There's no input for it. So you lose restore from snapshot, and then it just goes back. So how do we go forward? So in this case, I run it a few times. You can see the clock changes each time. So then I go to my solution. always use virtual environments. I should add that caveat. If you can use a virtual environment, please do. And so from there, we'll work on Angrypanda. We'll go into the virtual environment. And here we run the solve. And so what solver's doing is essentially interrogating the point. So we have an MMIO read, right, from the buffer, and it switches to symbolic execution. So this is when it returns from the clock. At that point, it uses Anger to explore n number of states forward, right? And then it returns explored all 4 paths, found 2 constraints. And so it found some binary decision being made between the code. At that point, we select one, right? We can arbitrarily choose one, or we can interrogate the code further, but we arbitrarily choose one specific path to interrogate, and then we go forward from there. So, and so at that point, we continue executing it, and it does that a number of times. So we actually end up having to halt execution, explore state, and return about 4 separate times. And this last one, we had 5 unique paths that we could explore. And we chose one, returning cache solution for address 1, MMIO read 6. We already had the buffer previously selected for that, or for that specific MMIO read. And then from there, we return the cache solution that we already solved for. And then we hit our defined solution address because we already know the solution address space that we wanted to get to. And we found the flag in virtual memory, which I think is rehosting is, what is it? Rehosting is the appetizer. Oh, rehosting is on the appetizer menu at Panda Express in LeetSpeak, which took me, I think that took me like 2 weeks to get because I didn't know you could just pull it from virtual memory, and then I had to programmatically find all the successful states and all this other stuff. But this is entirely dynamically arrived as well, which is awesome. You can explore code programmatically and just, it's great. Oh no, I pressed escape accidentally. Let me go back to presenting. Okay. So what can we do with this? Well, I wanted to visualize this because what's happening is kind of difficult to observe behind the scenes. And so what if we could just visualize it? Well, one thing we could do is we could actually build a constraint graph. And this is my kind of approach to it. Oh, mercy me. Just everything's happening, isn't it? Just everything. Okay. Okay, there we go. All right, so sorry, I have a hot corner and it activated. So let's say we wanted to activate, we wanted to build a constraint graph. Well, it's very simple. We're at a specific program counter, right? And we have our symbolic variable, and we can determine whether or not we continue execution or there's an error based on the constraint of that variable. So the edges in this case between our variable will be clearly marked with the constraint imposed upon the symbolic variable, and we can see how code is explored through this directed acyclic, no, it could be cyclic, directed graph. And this is what we get. It's pretty straightforward for the CTF time example, but we start at 0, 0, which is just an initialization value. Oh no, we're still showing a white screen. No. Okay, hold on, let me back out. I know what happened. Stop showing screen. Show. Okay, are you back on? You should see my PowerPoint. Okay, PowerPoint overview. Thank you. All right, there we go. Okay, good. Okay, so here's our constraint graph, right? We start at 0, 0 at the very bottom, and that's just an initialization value. From that point forward, we move up to hex 54C, and then we can see the constraints imposed on our symbolic variable. It looks like garbage, but basically it's saying if it's equal to 0 or if it's equal to the hex value 1337. Of course it's 1337. Of course that's what the clock's looking for. And so from that point forward, oh, go ahead.
It looks like every time you full screen into presentation mode, it goes white.
No, I can see your mouse. I've been giving the entire talk to a white screen.
No, not the entire talk. No, just okay. For 2 slides.
Okay, that's fine. That's fine then. Oh man, I thought I botched the whole thing. I can talk from here. This is fine. Okay, can you see this part?
Yes.
Okay, good. Then I'll just talk from here. Okay. So, whew, all right, good. So basically we go from our constraint solver. Man, that sucks. But we'll move on. but it's looking for hex 1337 within from the clock value, from the return value from the clock value. So that's actually the value it was looking for the first time. Well, we can set it and then continue executing, but it looks like it's just singularly, like regardless of which path we choose, it continues to execute here. Because in this case, I trimmed all of the the cyclical paths so we can get a single DAG, right? A single direct acyclic path. And so from here, regardless of which decision you make, you end up at this kind of fork in the road, right? And one leads you to an error. If it actually meets the constraint values set here, you'll get to an error state. And if you meet the constraint values on the left-hand side between these specific memory values of, I think, hex 18, hex 10, and hex 14, within those specific memory values within the virtual memory, you'll actually navigate towards this left path. You'll arrive at the program counter 57 or 570, right? And yeah, you just apply the constraints and then you can move and navigate towards your final solution. And what's really useful about this is that you can use that to annotate a control flow graph. So Anger allows you to construct control flow graphs from your, sorry, I'm talking with my hands, allows you to construct control flow graphs from your binary, but they are kind of out there. You can't really see what's going on. So what if we were able to take this and we were able to annotate this huge control flow graph? Well, you get a much simpler, much cleaner view of the execution, right? And it turns out all of this stuff, as we continue to explore it, was actually OpenSSL. So it actually looked for the key that was provided and then used OpenSSL to disassemble your code and execute. So it's pretty neat. As with all things, lunch is not free. There are issues, and there's a reason why not everyone, since 2016, not everyone has adopted symbolic execution unilaterally. Well, first, there's a state explosion problem. All right, you're looking at all states as you're continuing to execute, and that can be problematic. Loops are the prime offender in many cases, but most of the SE engines are pretty good about figuring out loops. Like, they're not going to sit there and constantly hammer on the same thing over and over, but it's something you need to be aware of, specifically if it makes small or minor changes within the loop, because it has to keep track of those as it continues to execute. And on top of that, it actually uses concurrency frequently in order to navigate multiple states at the same time so it can get wider coverage. But that is a huge expense, right? So it's going to kind of eat up memory. Second is speed. Not just that, it also takes a lot of time to set this up. Fuzzing also is not cheap. In fact, there's a huge effort in simplifying the time to set up a correct fuzz harness, because building a proper fuzz harness is an art form. It's a delicate art form that you have to do. Efforts like Fudge, I think from, which is I think embedded in OSS Fuzz at this point, take a step at that in order to get it kind of working a little bit easier, but it's still not a simple endeavor, and neither is setting up any of the symbolic execution stuff. So it does take time and it does take an investment, but it allows you to explore unique code paths and unique opportunities that fuzzing just won't hit in the same amount of time. And last is memory, right? Page faults in an emulated environment are problematic because it's not available for view. So you have to wait until the emulated environment goes out, grabs the page from memory and dumps it back in. And you have to be more conscious about that. And it's tricky. Oh yeah, does it scale? Poorly. So the next steps for me personally are to find more firmware examples for this and build a much more concrete and hopefully simple constraint graph that you can use to navigate and whatnot, to add more visibility to the software as you're rehosting it, because it's specifically targeting rehosting firmware. Optimizations, there's a ton of optimizations you can build into this, right? Specifically if you're going after very targeted or very simple firmware like Cortex-M firmware or ARM chips, that's a pretty good one too. Big, gigantic operating systems, it's kind of a lot to go at unless you're targeting a very specific application, but smaller IoT devices, this is great for. More Panda plugin integration and hopefully a big fancy UI. And then, yeah, that's it for me. I do have a few references, of course, like a good science kid. I do my references. But yeah, that's it for me. Oh, 47, 15 left. Not too bad, not too bad.
Yeah, I think that's perfect for questions. So does anybody have any questions for all of the magic that Chris just showed us?
I didn't mean to I didn't mean to confuse. I tried to really take the approach of I am a pen tester and I know what fuzzing is, but I don't know what any of this SE horse crap is. What can it do? And so I really tried to take it from that approach because it can be a lot, but it's actually really approachable when you try to play with it. It's pretty useful.
Yeah, so as somebody that works alongside some of the ex-Lincoln Lab folks that do this kind of stuff day in and day out, I've always thought it was like magic voodoo, and then your presentation, I'm like, wait, that makes a ton of sense. That's
Yeah,
super easy, super
yeah,
easy.
yeah, I know. Which one really linked it in for me? I think it was when I saw not the DARPA challenge, but it was when I saw someone basically find a magic value. Like it was just some super dumb embedded um, like character was looking for in the firmware. It's like, oh, we don't know what it is, but it's targeted. Oh, it's just a memory value. And then he fired up, I think it was anger. He fired up anger, grabbed it in like 2 minutes, just like fired up some dumb Python script, stopped right at the program counter, read virtual memory, and then looked at it. And it's like, okay, it should be this. It's like, what? And then we looked at the control flow graph and it had to be dynamically generated. So it was this gigantic wad and it just came out to like some stupid hard-coded password that you had to put in. I'm like, oh my gosh, that's so good. That's so easy. And so that's what let me like really dive in because the fuzzer's not going to find that, right? It's not going to find some super crazy contrived thing, but you could just ask the code, hey, what should this be? And it's like, oh, it should be this.
Yeah, right. Like fuzzing shows me where things are going to break and
Yeah.
how it reacts to values, whereas symbolic
Mhm.
execution is really demonstrating to me, like allowing me, like the phraseology that you were using, I think is perfect. It allows you to interrogate the code and like really figure out what it's doing.
Mhm. Mhm. And sometimes even answer the question for you, right? Because you don't like, for example, if it's trying to do some gigantic OpenS SSH decryption or function or some super hash, I just want to know what the hash is being compared to. I don't necessarily care how the hash is generated. You can just
Right.
ask what the hash should be, and it's like, well, okay, the hash should be this. It's like, oh, thanks, and you move right on. So yeah,
We did have a question in the Discord. Can you provide use cases? How have you find this specific thing useful?
okay. So explicit use cases I use for SE would be right now it's rehosting. And specifically ioctal calls because or syscalls because a lot of the times the syscalls are pretty straightforward, right? It returns 0 if it's bad or a constant error code if it's really bad, but it's bad in a way it expected, or return value, right? Like those are pretty known. But there's a variety of ways that you can but for more creative firmware a la RTOS's, a la like super tiny Cortex M firmware. It's just doing an ioctal call to peripheral, comparing that peripheral to something, some known constant it already knew, and then is continuing to execute. Or if that value isn't 100%, it will abort and you can't continue interrogating the code. So those situations are the ones that I kind of wrote this tool for, to kind of look at it, figure out what the ioctal call is actually going for, and setting it to that, and then continuing executing, like saving state after I set it and then continuing to execute. It's more of like a code exploration tool. Anger's used a lot in CTFs. It's used a lot in CTFs because it's very good at cracking open the code if you can't look at it in a like reverse engineering format, or if you want to ask specific questions of a reverse engineering or when you're reverse engineering. And I would say SE is probably more tightly coupled with a reverse engineering effort, right? As opposed to fuzzing. Fuzzing, you're like, well, fire at it and then we'll actually start reading source afterwards. I feel like, the results will show up when they do, and then afterwards we're going to start, evaluating it if it crashes. But I think that a reverse engineering effort, you really start interrogating what the code could be, possible input values to get there. Is this thing actually doing what it says it's supposed to do? And then in those instances, you might fire up something like this to help. I don't know if that. I hope that answered the question.
See, typing. We'll see.
Freaking out. I have heard that it is a bear to use. It's too much work. I have heard that argument before. It's too much work for something that fuzzing can just get done in a minute. Um, How do you defend, how do you defend against this probing? I don't know, man. Like, because I think RE is really, really strong. Like being able to crack open code. Now that Ghidra's free, now that RE is available to everybody, not just people with an idle license, like it's strong stuff. It's good stuff. And I think more people should be doing reverse engineering. But in general, I actually think it's really useful for very specific use cases where you need to figure out or have the code tell you something. That's when you can really just switch gears from exploring or from fuzzing or some sort of dynamic analysis and just go straight for that if you can do it quickly.
Yeah, I don't know that you can really defend against this kind of work, right? It's like unless the code is aware of how you're interacting with it and then
Oh,
does something.
I misunderstood the question. Yeah, how do you defend against this? Thorough obfuscation can bust it. Basically, if you
Okay.
have it state explode while it is trying to interrogate the source and figure out, for example, if there are too many constraints imposed upon the specific variable from the entry point. But yeah, you can just code around it. You just go, all right, cool. I don't care about any of that. If it works, then at some point your obfuscation will continue to execute and do what it's supposed to do without slowing down or without like significant slowdown. So you just halt there. You halt to when it's almost done, and then you ask it the question, hey, what are you comparing against this? Or hey, I noticed you reached out to virtual memory, or you had to do a page fault. What'd you grab while you were gone? Right, like things like that. You can just completely ask it for it. So it's really a strong tool in addition to reverse engineering or like analyzing analyzing the assembly. It's just really, really strong. It's just not useful all the time. That's the issue.
Yeah.
It's not a big fat tool that you can apply to everything. It's very targeted and it's very good at what it does. And when you use it for it, there's kind of not a lot you can do.
Awesome. Well, that puts us 6 minutes before the next talk.
Yes.
So I think we will wrap it up.
All right.
Thank you very much for the talk. I thought it was excellent. I hope others
Oh, thanks,
did
man.
as well.
No problem. Thank you, guys.
And
All
we
right.
will
Stop
see you in the
showing
Discord.
screen. All right. See ya.
Thanks. Bye.